Okay. Let's get started. Okay, answer to your names, please. Percy,
Here.
Burani,
Here.
Kilcrease,
Here.
Lackey is here.
Here.
Luna,
Here.
Macias, McKinnon is here. Morris is here. Powers, Renfrew, Salvador, and Spivey here. Okay, he's here. All right, before I begin, let me first apologize for an error I made in answering, a minor error in answering one of the questions in the last assignment. And I want to correct my mistake now. No, I've graded your assignments already. I haven't recorded them yet. I hope to get that done by this evening. Plus, I hope to, well, I will be able to send you back your graded work. If not by this evening, definitely by tomorrow, all right? But it's an answer to this question, number 9, in assignment number 2, where it says, what is the molecularity of step number 3? And I told you guys incorrectly that it's 1. I kind of suspected that I made a mistake because I've seen several students answer that question incorrectly. And then I went to the YouTube video to see what I actually said, and I didn't make that mistake. The answer should be 2, right? And the reason why, because you have 2 molecules of CLO reacting, all right, in that step, in that elementary step, all right? So if you have answered 1, I gave you credit because of course the mistake is on my part, but you need to understand that the correct answer is actually 2 for the molecularity of step number 3 in this mechanism right here, all right? Okay, so with that out of the way, let me go to what we'll be talking about today. We'll be starting chapter dealing with a very important concept, chemical equilibrium, because not only will we be discussing equilibrium in this chapter, but it's also going to be related to other topics that we'll be discussing in subsequent chapters, right? So a lot of the principles that we're going to learn in this chapter will apply to other topics when we start talking about acids and bases and sparingly salts and buffers and all that good stuff. Underlying how all those topics come together would be what we'll be discussing in this chapter, that is equilibrium, all right? Now, the first thing I want to mention here, and I don't think I have it here on the slide, is the fact that you need to understand what we mean first by what we call a reversible reaction, right? A reversible reaction is basically a reaction that will go in both directions. So let me give an example of that. A simple example of that would be let's see if this works. That's not working out. Okay, so a simple example of this reversible reaction kind of situation is H2 plus O2 to give H2O, right? And of course, the balance says we're going to need a 2 here and a 2 here. But you can also have H2O, 2 of that, reacting to form H2, 2 of that, plus O2, right? So in other words, you can go back and forth, right? You can have the H2 reacting with oxygen to form water, but you can also have water reacting by itself to form hydrogen and oxygen, right? And this is an example of a reversible reaction. Now, a shorthand way of representing this would be this. 2H2O, and then you have these two arrows pointing in both directions, and then you have 2H2 plus O2. So basically what we're saying, by using this symbol right here, we're saying that we can have the reaction going back and forth, right? And in truth and in fact, pretty much all reactions are reversible, right? The difference is, in terms of which one will predominate, the forward or the reverse reaction, is usually a matter of conditions. So for example, in the case of this reaction here, basically all we need to do in order for this to take place is apply some heat, normally in the form of a flame. So let me just put a flame here, right? Right, so if you have a mixture of hydrogen and oxygen in a vessel and you ignite it, then you have the spontaneous formation of water. Now, in the case of the reverse reaction, this can be done by a process called electrolysis. I don't know if you're familiar with that term. We will definitely be dealing with this particular topic when we get to the later chapter dealing with electrochemistry. But basically, electrolysis is using an electric current to split up a molecule or a compound, right? In this case, water would be what will undergo the split to form hydrogen and oxygen, right? So you can have the back and forth taking place. You can use conditions to favor one reaction going in one direction and use different conditions to favor the reaction going in the opposite direction, right? So that's what we mean by what we call a reversible reaction, all right? Now, in the case of equilibrium, which is the subject of this chapter here, equilibrium is a very special situation where we have a reversible reaction where the rate of the forward reaction will be equal to the rate of the reverse reaction, all right? So what we're talking about here, again, if you go back to the water example, you're going to have the back and forth occurring at the same time, right? But in the case of equilibrium, the rate of the forward reaction will be equal to the rate of the reverse reaction. And we have a graph here which basically illustrates what we're talking about here. So if we're plotting, and this could be for any reaction, if we're plotting the reaction rate versus time, all right? And let's say you start off with a certain amount of reactants, and as time progresses, as the reaction progresses, the rate falls and falls and falls until it flattens out here. And at the same time, you have no products to begin with, and the rate of the formation of the products will increase and increase and increase until it matches the rate of the forward reaction, right? So as it states here, at this point, where the time here is the time for equilibrium to be achieved, TE, the rate of the reverse and forward reactions will be equal, all right? So basically, those rates would basically be constant, pretty much forever, as long as the conditions remain what they are, all right? So basically, that's what happens in a state, in a case where a system is in a state of dynamic equilibrium, all right? So we're gonna look at this in more detail here. Now the question now becomes, okay, now that we know that the rates are the same, how can we prove that? Or, you know, if that's the idea behind equilibrium, how can we prove that there's still a back and forth taking place even after equilibrium? So here's an example that demonstrates this. So what we have here is, oh shoot, I can't write here. Okay, let me do this. What we have here is sodium chloride solid, which is here, in equilibrium with sodium chloride aqueous, because this sodium chloride aqueous solution is saturated. So we can represent that using this equation, NaCl aqueous, and then you have NaCl solid, right? So what we're saying here is that at equilibrium, you have the back and forth. Now, how do we prove that? Well, what one person did was add to this system already in equilibrium. This person add some solid sodium chloride, but this time the sodium in the sodium chloride is radioactive, right? So basically it emits radiation. And we're going to talk about radioactivity later on in, I think it's the last chapter of this course, all right? So basically, when you add this radioactive sodium chloride here, you can detect the presence of the radioactive sodium using a special instrument known as a Geiger counter, right? So what this person did was add the radioactive sodium chloride to this solution here. So it's a solid. So you'd expect that when it gets down here into the solid here, you'd expect some radioactive sodium chloride down here. But what eventually will happen if you wait for a while is that you're going to end up with some of the radioactive sodium chloride in the solution. So what does that indicate? That indicates that basically the sodium chloride is going back and forth between the solution state and the solid state, right, at equilibrium, all right? So that's basically one demonstration of the fact that the equilibrium is dynamic and not static. If it were static, then basically what will happen is that the sodium chloride that is radioactive will remain as a solid, right? And there'll be no radioactive sodium chloride in the solution, right? So we now know that this equilibrium here is a dynamic equilibrium and not a static equilibrium, all right? Okay, so, and this is just talking about, you know, what happens at the microscopic level. Basically, sodium chloride dissolves and recrystallizes continuously according to the equation here. So eventually some of the radioactive sodium will end up down here, well, end up in the aqueous solution. And that's why we observe what we observe there. Okay, okay, so let's look at some more quantitative aspects of equilibrium. So what is being represented here is a plot of concentration versus time for different components in a reaction. Now, the reaction that we're talking about here is the reaction of hydrogen iodide decomposing decomposing to form H2 plus I2. This is the equation that we're talking about here, all right? So that's the reaction that we'll be looking at here. We're looking at three different situations. Let me erase this here to avoid confusion. We're looking at three different situations, right? So the first situation here, we're looking at where we start off with 1.0 m of the hydrogen iodide, and there's no hydrogen or iodine to begin with, right? So of course, what will happen is that the concentration, as the reaction progresses to equilibrium, the concentration of HI decreases until it flattens out. At the same time, the concentration of H2 and I2, represented by this line here, will start increasing until you get to a constant value as well. So basically, after this time here, basically the system will be in equilibrium after that. And these are the equilibrium concentrations of HI and I2 and H2, all right? So that's what happens in this particular experiment 1. Now, in the case of experiment 2, you're starting off with a certain amount of H2 and I2. In fact, 1.0 m in each case, right? And you'll be starting off with no HI present. So what's going to happen as the system approaches equilibrium, the concentrations of H2 and I2 will decrease until it becomes constant, which means that the system achieves equilibrium. And at the same time, the concentration of HI increases until, again, when equilibrium is achieved, the concentration remains constant, right? So that's what happens in this case, where you start off with a 1 molar solution of both H2 and I2 and no hydrogen iodide starting off with, and you're going to end up with this situation. And these are the values for the equilibrium concentrations of both HI and H2 and I2. Now, the third and final experiment is dealing with a situation where you're starting off with 1 molar of everything, 1 molar of HI, 1 molar of H2, 1 molar of I2, right? And what is observed in this particular case is that the concentration of HI will increase, right? And it will increase until it reaches the equilibrium concentration. So what that is saying is that basically when you have that mixture, the reaction would favor the formation of hydrogen iodide, and therefore the concentrations of H2 and I2 would decrease as shown by this line right here, and then it flattens out again at equilibrium. So basically, the concentrations at equilibrium are given here. For the HI, that's 2.360 m, and for H2 and I2, they're equal to 0.320 m, all right? So that's basically what happens in the third experiment. Now, what we're gonna do is try to make sense of these numbers, all right? And see if we can predict somewhat the relationship between the concentrations at equilibrium, all right? So somebody decided to record the data associated with the different experiments that were conducted. Let me get rid of this here. Okay, so this is what they did. They started off with experiment 1, where, as I said before, initially you have 1 molar concentration of HI. You don't have any H2 or I2 to begin with, and then at equilibrium, you end up with these numbers, right, for the equilibrium concentrations of these, right? In the case of the second experiment, as we said before, we started off with H2 and I2 being equal to 1.00 m. In the case of HI, there are none of that present initially. And then when the system moves to equilibrium, you end up with these numbers here. And then in the case of the third experiment, we started off with 1 molar of all of these components, HI, H2, and I2, and then we end up with these equilibrium concentration values for the different components in that particular system. So to make sense of this, what this person did was that they decided to look at the ratio of the product of the products, the mathematical product of the products, divided by the concentration of the reactants. So this is the equation here. And then this person decided to put these numbers into that equation. And this is what this person observed. They get this value here, and this value here, when you plug in the equilibrium concentration values into this equation. Obviously, these are basically, you can't see any relationship between them. So what this person decided to do then, since there's a coefficient of 2 in front of the HI, they put a 2 here. Again, no systematic pattern emerges as a result of that. Then what this person decided to do is that instead of doubling the concentration of HI, they decide to square the concentration of HI, right? So in other words, the coefficient of 2 here becomes the exponent by which you raise the HI concentration to. And what do we observe? Very close correlation between the values as a result of that arrangement, all right? And this is what is observed for equilibrium systems generally, right? In fact, the next slide, let me just skip all this here, is basically a general statement of what is observed, right? So if you have this hypothetical example, right, of a system already in equilibrium, then we can write down what is called an equilibrium expression, which looks like this. Generally speaking, it is the product of the concentration of the products divided by the product of the concentration of the reactants. However, you have to ensure that in each case, you need to raise the concentration of each reactant and product to the power of the coefficient in the balance equation, right? So the lowercase letters represent the coefficients, the uppercase letters represents the substances, and basically, as you can see here, the concentration of this product G is raised to the lowercase g, the concentration of this product H is raised to the lowercase h, divided by the concentration of A raised to the lowercase a, times the concentration of B raised to the lowercase b, all right? So that is basically a general expression for the equilibrium expression if you're given a balance equation, which underscores again, as I've always said, the importance of balancing equations, right? If the equation is not balanced, then basically this expression will not be correct, and therefore your subsequent answers based on that is more than likely going to be incorrect, all right? Okay, now there's a special name given to the Kc constant that is seen here, right? It's called the equilibrium constant. Hold on 1 minute. Right, so Kc, hold on 1 minute. Right, Kc is called the equilibrium constant, all right? And what you're going to see is, and more specifically, I should add, it is the concentration equilibrium constant, right, Kc. What you're going to learn is that there are other equilibrium constants which are based not only on concentration, but based on other aspects as well, such as pressure, and then there are some other K expressions which you're going to learn about, right? So this one is specific because the equation, as I showed you earlier, basically relates Kc to the concentrations of the different components in the system at equilibrium, all right? Okay, so a couple of things about the equilibrium constant listed here. Firstly, that this equilibrium constant will be constant regardless of the initial concentrations of the reactants and products. And we saw that demonstrated in the reaction I showed you, the reaction of H2 plus I2 to give 2HI. In different situations, they start off with different amounts of reactants and products. And ultimately, when the system achieves equilibrium, Kc is approximately the same, all right? This is a symbol for Kc. And whenever you're writing the Kc expression, it's always the terms for the products divided by the terms for the reactants, right? So it's products over reactants, all right? Another thing too, I mentioned this before, is that the power to which the concentrations are raised in the equilibrium expression are the same as the coefficients of those substances in the balanced equation, all right? Okay, so those are some important aspects. There's one important aspect which I come to think of it, which I probably should include. Let me write this down. And we're gonna see how that works later on. So the fifth point here is that Kc is constant as long as the temperature is constant. All right, that's another important aspect of Kc that we're going to see how Kc is affected by temperature later on. But for now, just keep in mind that Kc value, right, is dependent on the temperature of the experiment or the temperature under which you obtain the experimental data and so on. So what you're going to notice is that in a lot of these questions, they would give you a temperature, just emphasizing the fact that Kc is temperature dependent. All right. But Kc doesn't change otherwise, right? It doesn't change if you change the initial concentrations of different substances. If gases are involved, the pressure, initial pressure doesn't change. You know, the only factor that will change Kc is temperature. And later on, we're going to learn how to make predictions as to how temperature affects the Kc value. All right. So let's look at this example right here. It says, if the equilibrium concentrations of COCl2 and CO2 are the same at 395 degrees, find the equilibrium concentration of CO in the reaction. So they gave you the equation here, which is balanced. Always check to make sure that the equation is balanced, right? And they gave you the Kc value be equal to 1.2 times 10 to the 3, right? So to answer this question, the first thing I would do is I would write down the Kc expression for this reaction. So let me ask you, based on what we have learned so far, what would be the Kc expression for this reaction?
Concentration of CO times the concentration of CO2. No, sorry, concentration of CO to CO2.
Okay, all right, because remember it's products over reactants, right?
Yes.
Divided by?
The concentration of CO times.
Concentration of?
CO.
CO2, right? And that's it. Okay, so that's equal to Kc. Now the question says, if the equilibrium concentrations of COCl2 and Cl2 are the same, find the equilibrium concentration of CO. So what this question is saying is that this and this are the same. So they will cancel out, right? So therefore, this would imply that Kc is equal to 1 over the concentration of CO. But the question is asking for the concentration of CO, right? So that would be equal to 1 over Kc. So 1 over 1.2 times 10 to the 3 would be the answer, whatever it is. So let me get my calculator. I can find it. Okay, so 1 over 1.2 times 10 to the 3 is what we're looking for. 1 divided by 1.2 times 10 to the 3. And according to my calculations, rounded off to 3 sig fig, the answer will be 8.3 times 10 to the minus 4. All right? So that's basically how that works. Now, one thing I'd like to mention, all right, and this is something that is commonly practiced when it comes to calculating equilibrium constants and so on, is that when it comes to calculating Kc's and the other K's that you're going to learn about, you don't have to worry about units, all right? Now, there's a long story behind it. All I remember is that when I was in college, we had to be concerned with units. This is way back in the dark ages, I won't tell you when. And then all of a sudden, when I started teaching, and I started checking out textbooks, they don't worry about units when it comes to calculating Kc or the other Ks that you're going to learn about. So that's why you see that there are no units associated with the Kc value that is given, all right? And this is basically common practice. And there's a good reason behind that, but I won't go into that right now, all right? Okay, any question about this? Any question? Any question? Okay, so, Or I should clear this first. Okay, so let's have some more fun with this. Now, what happens when we modify the equation representing the system in equilibrium? Okay, so let's say you're given this equation right here, for example, right? Already balanced. And the Kc expression, we know how to write it based on what we have just done, right? Kc will be equal to the concentration of NO2 squared divided by the concentration of NO squared times O2, right? And it turns out that this was determined to be equal to 4.67 times 10 to the 13 at 298. Kelvin, and let me just say that usually when people are quoting, but not in all cases, but usually when they quote Kc values and other K values, usually it's that 298 Kelvin or 25 degrees Celsius, but not always, all right? Okay, so this is the Kc expression for this equation as it is written, right? So what if you're given this equation, right? How would you determine the Kc for this equation based on this equation and the Kc for that equation? Now, my first question to you is, compare these two equations, compare this to this. What do you observe is the difference between them? I'm sorry? Exactly. You're flipping the reactants and products. So the question now becomes, how does that affect the Kc value for this in relation to the Kc value that was given here initially for this reaction? Well, what we can do is write down the Kc expression for this, and that would be, and we're going to call that Kc prime, just to make a distinction between the new Kc value and the old one, right? So if you were to write down the Kc expression for that, what would that be equal to? Not 2 NO2, well, firstly, NO squared, I'm sorry. Because remember, you need to raise the concentration of the reactant or product to the exponent, its coefficient, right? So you were saying NO, concentration of NO squared. Hmm? No, but what about O2? What did you, I'm sorry, what did you just say?
So it would be NO square and O2?
Right, okay, I'm sorry. I didn't hear you right. So concentration of NO squared times the concentration of O2, and then what? Over concentration of NO2 squared, right? So therefore, this is what you're going to get. And if you compare this to this, what you'll see that this would be equal to 1 over what Kc is equal to. So Kc prime would be equal to 1 over the old Kc. So basically, all you have to do is put 1 over the Kc. They gave you that value for the old Kc, and then you do your number crunching, and you end up with your new Kc value, all right? And this is a general rule, for which there are no exceptions. Basically, the Kc for the forward reaction would be equal to 1 over Kc for the reverse reaction, all right? So that's basically the consequence of that. Okay, any questions about this one? Any question? Any questions? Any questions? No questions? Okay, moving along. Same equation we're starting off with again, same Kc value, right? But this time, the new equation is this. All right? So again, my question to you is, what's the relationship between the new equation and the old one?
Some reactants are flipped, but the coefficient for the O2 is a half.
Well, not only for the O2, for everything. All right? So what you just said, the first part is totally correct. We flip again the reactants and products, but now all the coefficients, in addition to that, all the coefficients are now divided by 2. All right? So let's see, how would we determine the new Kc for this equation? So we're going to call that Kc double prime. So before I put it on the screen, let me hear what you guys think would be the equation for the new Kc, which would be Kc double prime. Concentration of NO times concentration of O2 raised to the half divided by concentration of NO2, exactly.
P2 NO2?
No,
Okay.
no.
I'm looking at your PowerPoint and it has it to the squared. When you do it next.
Yes, that would be incorrect. Thank you for pointing that out. Yeah, so please make a note of that, folks. This two here should not be here. All right? Because there's no two there, all right? But this is the equation right here, right? For the KC expression, for the new equation that is written, right? So basically, in addition to flipping, which results in the KC, the new KC be equal to 1 over KC, you also have to find the square root of that because all the coefficients were divided by 2 from the old KC, or from the old system to the new system, all right? So the KC double prime will be equal to 1 over KC raised to the half. So that means that, basically, well, we know that 1 over KC already from the previous example is equal to 2.14 times 10 to the minus 14. So all we have to do is find the square root of that, and that will be equal to 1.46 times 10 to the minus 7, all right? So that's basically how that is done. Okay, any questions about this one? Any questions? Any questions? Okay, so just to summarize a couple of things that we just learned. Firstly, for the reverse reaction, the K for that reaction would be 1 over the K for the forward reaction, all right? If the equation is divided by 2, then the Kc for the reaction would be the square root of the Kc for the original reaction. And the general rule is that when the coefficients of an equation are multiplied by a common factor n, right? So n could be any number. Then we raise the Kc value to the power of n to obtain a new equilibrium constant, right? So if you multiply right through by 2, then the new Kc value will be squared. If you multiply right through by 3, the new Kc value will be cubed. If you multiply right through by half, then the new Kc value will be raised to the half, which would be square root, and so on and so forth, all right? And again, very important, you must start off with a balanced equation. If the equation is balanced, or I should say, if the equation is not balanced, then the Kc expression would be incorrect. And therefore, any subsequent calculations based on that would more than likely be incorrect, all right? Okay, so let's look at this example right here. They gave you this equation, which is balanced, and they gave you the Kc value, which is 7.07. So the question is now asking, what is the value of Kc for the reaction? And it gives you that equation, right? So what would you say is the answer to that question for the A part? What's the first thing you observe when you compare the first equation to the new equation for A? It's flipped, right? So how would you determine the Kc value? Turn this on. I'm going to call this Kc prime. So how would you calculate Kc prime?
1 over 7.
1 over 7.07. So 1 divided by 7.07. So according to my calculation, that would be equal to 0.141. Okay, what about the second equation? What do you notice when you compare the first equation to this one in B?
The coefficients are all different.
All the coefficients are what?
Multiplied by 2.
Exactly. So therefore, I'm going to call this Kc triple prime, or double prime, I'm sorry. So how would we calculate, based on that, based on what you just said, how would you calculate the new Kc value, Kc double prime?
Multiplied by 2.
Nope. What did we just say? If you multiply the equation by 2, what happens to the Kc value? Square, exactly. So it would be 7.07 squared. All right, so 7.07 squared, according to my calculation, is equal to, run it off to 3 sig figs, would be 50.0. And that's how you do that, all right? Okay, any questions about any of those examples? Any questions? Okay, so I'm going to give you assignment number 3 now to get started on. And I'll tell you what questions you need to focus on for the time being. Oh, I almost forgot.
Thank you.
For you guys out there in Zoom, I'm not sure if I published assignment number 3, so let me do that now if I haven't done that yet. Assignment number. Okay, so assignment number 3 is now published. So you guys out there in Zoom can get started on that. Now, the questions I want you guys to focus on are questions 1, 2, and that's it, 1 and 2. All right, questions 1 and 2. In fact, let me bring this up. Let me first. Let me bring this up so that we can look at it together. Okay, so I'll probably help with the first 2, and then you can do the rest. Okay, so the question is asking for the equilibrium constant expression for Kc and Kp. Now, don't worry about Kp yet, right? Kp we're going to talk about shortly, right? So let's focus on Kc. So turn this on. Okay, so what would be the Kc expression you think for the first one? Kc is equal to what? Concentration of Hi squared divided by concentration of H2 times the concentration of I2. All right? Okay, what about B? Kc would be equal to what? Concentration of HCl raised to the 4th times the concentration of O2 divided by concentration of Cl2 squared times concentration of H2O squared, all right? Okay, very good. So if you understood that, then you should be able to do the others in that section. So work on that, and if you have any questions, feel free to ask. So you should be able to do C, D, and that's it, yeah, C and D. So do that now. Here. In the meantime, let's see who came in late. Macias is here. Powers is here. Renfro. Is Renfro here? Nope. Salvador is here. And Spivey is, oh, I got you already, okay. Okay. Okay, so are we finished with the first one? All right, so let me scroll down to number 2. So in the case of number 2, they gave you this equation and they gave you the Kc value for that equation, right? So they're asking now for the Kc for some other equations, which are derivatives, or if you want to call it that, for the first equation. Okay, so for the first one, what do you think the answer is? I'm going to call this Kc prime. Now, this is the Kc value for this equation, right? So what you should do is be comparing this equation here to this equation here. What do you notice?
It's flipped.
It's flipped, right? So what does that mean? KC prime would be equal to what? 1 over 0.145. So what does that give? 1 divided by 0.145. According to my calculation, this works out to be equal to, rounded out to 6.90. And again, please correct me if I'm wrong. So, do the calculations along with me. All right, what about B? I'm going to call this KC double prime. Now, let's compare this equation to the first one. Now, what do you notice?
Double.
Everything is double. All the coefficients are double, right? So what does that mean for the KC double prime calculated based on that?
Square.
Exactly. So the 0.145 squared, whatever that gives. So 0.145 squared, and according to my calculations, squared. According to my calculation, this would be equal to 0.0210. All right. Okay. And then let me scroll down to, so that was B. I take it I can clear this, right? All right, so in the case of, oops, scroll down some more. Okay, so we have 2 more, C and D. So in the case of C, okay, so comparing C to the first equation, which I don't have, what do you notice? I'm sorry?
The coefficients are.
Okay, so what does that mean? I'm going to call this KC triple prime. What does that mean for KC for this equation? KC will be equal to what? The square root of 0.145. So 0.145 square root. Okay, the answer I got is 0.381. All right. And then for the last one, D, how would you, I'm going to call that KC 4 prime, all right? So how would you calculate that value? Based on, in fact, to make life easier, if you compare this equation to this equation, you see that basically this equation is a flip of that one, right? So you could actually manipulate this to get the answer here. So how would you calculate KC 4 prime? 1 over, right, so 1 over 0.381, whatever that gives, so 1 divided by 0.381. So the answer I got is 2.62. All right, so that's basically how that is done. Okay, any questions about any of these? Any questions? Questions? All right, I think it is okay for me to clear this as well. So let me go back to the PowerPoint. And what shall we talk about next? Okay, now here we have some more interesting situations here. Now, what we have here, this question is asking for us to calculate the KC value for this equation right here, right? Now, they gave us, in addition to that equation for which you need to find KC, they gave us these 2 equations and their respective KC values. So what the question is asking for us to do is to use these equations along with these KC values to determine the KC value for this equation here, right? Now, if you look at this equation here and compare it to these 2, what you'll notice is that when you add these 2 equations, this one and this one, you're going to end up with this one. In fact, let me do this separately. All right, tell you what, let me. Copy this and put it. Okay, so that's one equation, and then the other equation is And then the equation for which you're trying to find Kc, I'm gonna copy that as well. That's this equation right here. And I'm going to put that above. Okay, so these, let me make this bigger. Okay, so these are the equations. Okay, so these are the three equations. They gave you the Kc value for the second and third equation. But now they're asking for this. Now, as I was saying, if you compare these first two to the third one, what you'll notice is that if you add these two equations, the two NOs will cancel out, and you'll be left with N2O plus half plus 1 gives you 3 over 2 O2. And then on the product side, you're just going to have 2 NO2. And what you'll notice is that this is the same thing as this equation. So the question now becomes, how do we determine Kc, given that when you add these two equations here, you're going to get this equation. How do you determine the Kc for that equation? Okay, so what I'm going to do is, and this might take up some more space, so let me scroll down. So what I'm going to do is write down the Kc expression for the first equation. Kc 2 is equal to what? Tell me. Kc2, concentration of NO squared, not NO2, right? Product over reactant, divided by
Concentration of N2O.
concentration of N2O times,
Are we looking at the one above?
we're looking at this one right here. Kc2. So that's this equation, this
okay.
equation right here, right? So, you said something? Or somebody said something, I don't know. What about the O2? How do we factor that here?
Concentration of O2 to the power of 1/2.
Exactly, okay, very good. So that's Kc2. Now Kc3, what's the expression for Kc3? Equals the concentration of NO2 squared divided by concentration of NO squared times concentration of O2. Very good, all right. So let's see what happens when we multiply Kc2 by Kc3, right? You're going to get concentration of NO squared divided by concentration of N2O times concentration of O2 raised to the half, multiplied by the expression for Kc3, which is concentration of NO2 squared, divided by concentration of NO squared times concentration of O2. And what happens? Well, for one, the NO squared here will cancel out the NO squared there, right? And this O2 raised to the half will multiply by O2, so that will give you O2 raised to the 3 over 2. So basically, you're going to end up with concentration of NO2 raised to the 2 divided by concentration of N2O times concentration of O2 raised to the 3 over 2. And if you look at this carefully, you'll see that that would be equal to the Kc expression. Let's go back up here. That would be equal to the Kc expression for this equation right here. The concentration of NO2 squared divided by the concentration of N2O times the concentration of O2 raised to the 3 over 2, all right? So basically, what we're saying here is that if you have two or more equations that add up to give you one equation, then basically the Kc for that new equation resulting from the addition will be equal to the product of the Kc's of the separate equations that are being added to each other, all right? So basically, KC1 will be equal to KC2 times KC3. All right, and that will become important later on when it comes to doing certain calculations. All right. Okay, any questions about this? Any questions? Any questions? Okay, so let me go back to the PowerPoint here. So this is basically stating what I just said, right? When you when you add the equations to give the final equation, then you have to multiply the corresponding KC values to get the KC for that final equation. All right? Okay, that is it. So let me see here. Okay, can't do anything here. All right. So let's talk about situations where gases are involved in equilibrium systems. All right. So of course, because we're dealing with gases, it's more convenient for us to make measurements of pressure instead of concentration, even though pressure can be seen as a proxy for concentration because they're directly related to each other, right? But it's more convenient to measure pressures of gases than to determine concentration. So therefore, as a result, there's another equilibrium constant that is used for gaseous systems. It's called the equilibrium constant for partial pressure of gases, right? And basically, it's the same arrangement as in the case of KC. The only difference is that we just put in the pressure terms, right? So in the hypothetical example that I gave you before, these are the values for the pressure of the different gases, and they're all raised to the coefficients of the different components in the balance equation, right? So we call that constant Kp to distinguish between that and Kc, right? So Kc is in terms of concentration, Kp is in terms of the partial pressures of gases, right? Now, we can use Kc for gaseous systems, right? But as I said before, it's more convenient for us to use Kp. Kp, on the other hand, can only be used for gaseous systems. So we cannot go from Kp for a gaseous system to, let's say, an aqueous solution system. We can't apply Kp to that because there are no gases involved. Another thing I need to mention too is that there's a relationship between Kc and Kp, which I think we're going to get to right now, right? So this is the equation here which relates Kc to Kp, right? So if you have a totally gaseous system, excuse me, and you know what the Kc value is, and you know what the Kp value is, then this is the relationship here between Kp and Kc. Kp is equal to Kc times, and in parentheses you have RT, R being the monogas constant. In this case, the monogas constant will be one that you'll be familiar with from your Chem 1. R would be equal to 0.0821 liters atmospheres over mole Kelvin. That's the value of R you'd use here, right? And let me explain something about delta N here, because that combination or product of RT must be raised to this number here, delta N. Delta N is a difference between the sum of the coefficients and the sum of the coefficient of the products and the sum of the coefficients of the reactants, right? So this is the equation for calculating delta N. It's the sum of the coefficient of the products minus the sum of the coefficients of the reactants in a gaseous system, all right? So that's delta N. So that's the relationship between Kc and Kp. Let me see here. Oh, so we can go back now to question number 1, because remember question number 1 is asking for you to calculate Kc, which we have done already, right? So now we need to calculate Kp, because the question asks that as well. So let me clear this and go back to the assignment. Okay, so I'm scrolling back up to question number 1. So let me help you with the first one. So for the first one, KP would be equal to the concentration, not concentration, I'm sorry. I'm making a mistake already. It's the pressure of HI, and that will be squared because of the two here, divided by the pressure of H2 times the pressure of I2. And that's it, right? So similar arrangement in terms of the terms for the different components, but you're using pressure terms, not concentration terms, because you're calculating KP. So let me hear what you have to say for B. What is KP for B? Pressure of HCl raised to the fourth times pressure of O2 divided by pressure of Cl2 squared times pressure of H2O squared, and that's it. All right? So based on that, you should be able to do the rest. So you can just work on that right now. Again, if you have any questions, let me know. Can I clear this? So you guys now should be able to do C and D in terms of the expression for pressure. Okay, finished? All right, so I have a question for you. What if delta N, which is this right here, is equal to 0? What would be the consequence of that? If delta N is equal to 0,
Does that have to do with like,
hmm?
like there has to be a 1 somewhere?
Well, anything raised to the 0 is equal to 1, right? So if RT is raised to 0, then what's the result?
Should be one.
Hmm?
RT equal 1.
Okay, and therefore, you're right, RT raised to the delta N is equal to 1. So what's the result of that? KP would be equal to KC, right? So whenever you have delta N, which remember is the sum of the coefficients of the products minus the sum of the coefficients of the reactants. If that's equal to 0, then KC would be equal to KP. And that can be seen, for example, in, I'm sorry, let me get out of this here. The first, this one right here. This equation right here. The sum of the coefficient of the product is 2. So delta N would be equal to the sum of the coefficients of the products, which is 2, minus the sum of the coefficient of reactant, which is also 2. So that would be equal to 0. So therefore, in this case, KC and KP would be equal to each other. All right? Okay, so I just thought I should point that out. All right, so let me clear this. And let me do this, and let me go back to the PowerPoint and on to, okay, I'm not sure if we'll have enough time to complete this example, but I'm going to try. So they gave you this equation and they gave you the KP value for this. So the question is asking for the KC value. Now remember, KC KC is equal to KP times RT raised to the, hold on. I think I probably have it wrong. Hold on. It should be KP is equal to KC times RT raised to the. So it should be KP is equal to KC times T raised to the delta N. All right. So the question is asking for the KC value for this reaction. They give you the reaction and they give you the KP value. So based on this expression here, we can rearrange it to get KC is equal to KP divided by RT raised to the delta N, right? Now the KP value is given as 0.660 divided by RT. R is 0.0821 times T, which is 319 Kelvin, that's given. And this would be raised to, this part here would be raised to delta N. So what is delta N in this case? What is delta N? Remember, delta N is the sum of the coefficients of the products minus the sum of the coefficients of the reactant. What's the sum of the coefficient of the product? 2, right? And what's the sum of the coefficient of the reactant? 1, right? So basically delta N here would be 2 minus 1. All right? And then, well, that would obviously be equal to 1, so 0.66 divided by 0.0821 times 319. Okay, so according to my calculation, the A part works out to be 0.36 fix. 36 fix, so that's 0.0252. All right, so that's the A part. Okay? Now the B part is asking, what is the value of KP for the reaction? And it gives this reaction, gives this equation here. Okay, so when you compare this equation to this equation, what do you observe? It's flipped, right? So what would be the new KP? I'm going to call that KP prime. What would be the relationship between the new KP and the first one? What's that? If the equation is flipped, what happened to the K value? It's inverted, right? So that would be 1 over KP. So 1 over the KP value, which is 0.660. So 1 divided by 0.660. And the answer I got is 1.52. All right? So that's for the B part. And then now for the C part, I'm going to see if I can squeeze it in here. It says, if the equilibrium partial pressure of NO2 is 0.332 atmospheres, what is the equilibrium partial pressure of N2O4? Now, the equation which relates KP to partial pressures in this case would be KP is equal to the pressure of NO2 squared divided by the pressure of N2O4, right? Now, what the question is asking for is the pressure of the N2O4. So the pressure of N2O4 would be equal to pressure of NO2 squared divided by KP. I'm running out of space. I'm just going to continue up here. All right. So basically, the pressure of N2O4, which is what the question is asking for, would be equal to the pressure of NO2 squared. So that's 0.332 squared divided by Kp, which is 0.660. So let's see what that gives. 0.332. Oh, by the way, this should be squared, right? Okay. So 0.332 squared. Divided by 0.660. So according to my calculations, this works out to be 0.055, 0.0554. And that would be the answer for the C part. Okay, I'm sorry for the jumbled mess in this case. I just didn't have enough space to write everything out neatly, all right? Okay,
I got something.
Oh, you got something different? Okay, I could be wrong.
1, 6, 7.
So you're talking about what part here? You're talking about here?
Yeah.
Okay, let me do this again. 0.332, and that's squared. Oh, I pressed the wrong button. That's squared, divided by 0.660. I pressed the Q button when I should be squaring it, so. You guys are right. So let me just scratch this out. And you got 0.167, right?
Yes.
Okay, good. Okay, so that's basically how that is done. All right, I'm gonna stop here. Let me just check this here and see what other questions you can possibly. Okay, so based on what we have covered, you should be able to do questions 3. And that's it, question 3. So work on question 3. If there are any problems, have any questions while working it, let me know before you leave. So, somebody was asking about, what you should do in order to prepare for test number 1. Well, I'll be sending you guys your assignments graded this evening, all right? Or definitely by tomorrow morning. So you can review that. Review also the answer key, which I'm also going to publish. Review the assignments, right? So the assignments would be assignments number 1 and 2 I'm about to send you. And in addition, I would highly recommend that you do as many problems from the textbook, right? The chapters dealing with kinetics and solutions. Each of those chapters have more than 100 questions. I don't expect you to do all of them, but if you do as many as you can, then that should also help you in terms of preparing for your test, all right? So just to let you know, that test will be on next week, Wednesday, all right? And it's going to have at least 3 questions. I don't think I'm going to put more than 3 questions. And I think, I posted a past test? Yes, okay, so you can review that as well, all right? So, if you do that, you should be in good shape. Of course, I'm available during office hours if you have any questions. Please feel free to come by or contact me via Skype, and I'm more than willing to help you. All right, folks, so that's it for today.
The password? Yeah. Yeah, all right.
What's up?
I forgot.
So this looks like a collective property lab. Okay, make sure you write the name up here so that I know it's you. And I should talk to you guys about that too. So you guys not following the rules for submission of assignments. Anyway. Yes, ma'am.
I don't know if, because we will be done from Monday to Thursday.
Oh, well, unless you can link up via Zoom. The other way I can, yeah. Because I do plan to have the Zoom option available.
So like assume and just like the test.
Oh, you're talking about that?
Yeah.
Oh, I'm sorry, I thought you were talking about the event. I'm sorry, my bad.
Okay, sorry.
My brain is. Oh, so you're saying that, well, you could, could do the test later.
Okay.
So you say you'd go from when to when?
From Monday to Wednesday, so. When is it? We go Wednesday, right?
It's Wednesday.
Yeah,
at
we're
this
leaving
time.
on the tenth, so Monday and.
Next week, Wednesday?
Yes. Well, let me ask you this, will you be able to, do the test? Will you be able to come by on Friday?
Yeah.
Okay,
Yeah, I can do it.
all right, let's do that.
Thank
But
you.
remind me.
Yes,
Like,
I will.
send me an email like the day before, so I remember.
Okay.
Mhm.
I printed out the power test that you posted.
Mhm.
Is it gonna be similar to that?
Yeah,
Is
similar,
it the same thing with different numbers?
no. But I mean, similar types of questions, where, you have to show your work and so on, so.
Okay, so
It
just,
won't necessarily be the same questions. If it's gonna be the same questions, that's totally by accident. But, that's why I said that, you guys need to, practice solving problems so that you'll be in good shape for that,
okay, thank
for
you.
that test. All right, take care.
Thank you. I got it.
Those of you out there in Zoom, I'll be signing off right now.